Hi, welcome you all. So today we'll be discussing briefly on the topic fault plane solutions. Yeah, now coming to why I have chosen this fault plane solutions. This is one of the important topic in the syllabus structural geology and tectonics for the second semester. So I hope this lecture will give you a thorough understanding of the fault plane solutions and the importance. Now coming to what we are going to cover in this lecture. So before going to the fault plane solutions, we should understand one of the important topic called focal mechanism of an earthquake. So first I will start with what is the focal mechanism of an earthquake. Then I will go to what is the fault plane solutions and what does this fault plane solution give us. Why do we need to bother for this FPS? Then we'll go for the basic idea of the mechanism involved in calculating this FPS, and after that finally we'll get an idea of what is the benefit of doing such a fault plane solution methodology. Yeah, now coming to the focal mechanism. So what is the focal mechanism? Focal mechanism of an earthquake describes the type of deformation in the source region that generates the seismic waves. Now coming to what actually focal mechanism means, it means that here we try to understand what is the deformation that lead to the generation of the earthquake. Generally earthquake will occur because there will be some kind of movement along some planes which are which occur below the surface of the earth. Now these planes along which movement occurs, these are the planes along which the rocks will break and move past each other, so these are called the fault planes. So here in this figure we can see a causative fault plane. So this plane, along this plane there was some kind of movement, and this movement is shown by these black arrows. Now as this movement occurred, after that there was liberation of the energy from these red points, and this liberation of energy that propagated from this source region, and that will shake the ground and lead to the formation of the earthquake. So as this earthquake propagates, we have some kind of instruments on the surface of the earth, as we see from these blue triangles. So these blue triangles are called seismometers. In these seismometers we record the earthquake. So we can see here some kind of records. So these records we give the seismic wave as a function of time. So this will give us how the surface vibrated due to the propagation of the earthquake. So we have a number of seismometers we can see, like here we are seeing the two seismometers at distance. So from this, as the earthquake occurs, we can see how these waves moved and how the vibration was recorded in the seismometers. So what does focal mechanism gives? Focal mechanism gives the mechanism which led to the formation of this earthquake. So what is this mechanism? This is the displacement of the rocks along this causative fault in the source region. So what we will understand from the focal mechanism, so from this focal mechanism we will get to know what kind of displacement have taken, what is the sense of movement, and what is the direction of the movement, like what type of fault is that a normal fault or a reverse fault, what was the strike of the fault. So the focal mechanism will include almost every aspect of the deformations which are related to the source region that generated the seismic waves. So next, coming to the fault plane solutions. So what is actually a fault plane solution? So fault plane solutions, which are also called the focal mechanism solutions, this simply refers to a method in which the seismograms from the areas surrounding the earthquake epicenter are used to study the faulting process. So we have seen that the earthquakes are generally related to some kind of causative faults. So we have seismometers in different places, and from the seismometers which are surrounding the epicenter of the earthquake, we can find out what is the causative mechanism using these fault plane solutions. So what does fault plane solutions give? So it basically gives us the focal mechanism, that is the geometry and the sense of motion of the fault. And why is it required? Because if we know the sense of motion, then it will act as a vital tool for understanding the processes occurring at the plate boundaries. So what happens in the plate boundaries, we see that there is different kinds of deformative forces that leads to the formation of faults or thrust. So they are more prone to the earthquakes. So if we know the focal mechanism, we can understand what kinds of faults are related to the earthquakes, what are their signs, and what kind of movements are occurring in those faults. Yeah, now we will try to get a brief idea of the mechanism how FPS fault plane solutions work. So for understanding this, let us have a look of an spatial map. So in this map we see a red color dot here. So one earthquake, we suppose that one earthquake has occurred whose magnitude is around 6.6. So as this earthquake occurs, there was some kind of movement, subsurface movement at this place. Now this movement is seen in this right hand side figure. Now here we see that there is a subsurface fault, and in this brown part, just in the bottom of the fault, there was some kind of movement which is shown by this arrow. So this is a reverse fault, and due to this movement this earthquake has occurred. Now what happens, as the displacement occurs, one block moves up and the other block moves down relative to the fault plane. So the block which moves up, there will be slight upliftment in the surface, and in the block which moves down, there will be somewhat downward movement in the surface. This is shown in by the red color and the blue color arrows. The same thing is also seen in the seismometers which are scattered in the surrounding region of the earthquake. Here we can see the sense of movement as shown by these black color arrows. So in the right hand side we can see somewhat upward movements. So this upward movement which is seen in the right hand side by this red color arrows, these are seen as these black color arrows in this spatial map. Similarly, in the left hand side of the fault plane, we are seeing that there was some downward movement, that is the blue color arrows. So similar movements are seen in the spatial map in the seismometers, which are seen as downward black color arrows here. So as this earthquake occurred, there was propagation of the seismic waves. Now there are different kind of seismic waves, S waves, P waves. Now P waves are longitudinal waves, so they will have a compression and tension. So there will be a repeated cycle of compression and tensions in the longitudinal waves. Now as this wave propagates, now the block which moves up, so the first arrival P waves will be of compressive nature in this places, but the block where it moved down, there the first arrival P waves will be of tensile nature. So if we understand the P wave signature, then we can find out what kind of movement, subsurface movement has taken place. So this is the first prime importance of the fault plane solutions. So basically the fault plane solutions gives us the sense of movement along the fault from the kind of P wave the P wave velocity, P wave movement recorded in the seismometers. So now we have an understanding that the first appearance P waves on the surface will be dependent on the kind of movement that has occurred on the subsurface. Now we will try to make a mathematical model which will give us the type of deformation that has led to the formation of the P waves. So how we will make a model? So it will be in the form y is equal to f of x. So what is y here? Y is our output and x is the input. So what input we generally give? Input is the radiation pattern of the energy emitted by the crustal earthquake. So whatever earthquake has occurred, it has radiated some kind of energy. So those energy was recorded in the seismometer as the P waves. So the P waves which were recorded, those will be fed as input into this model. So what we will get from this model, we will get the output as y. So this output y will be the solution of the moment tensors. So this model actually will give us the moment tensors of the earthquake. Now what is a moment tensor? Moment tensor means these are the couple, these two forces. Now what is a tensor? Tensor we have already discussed in our previous class. These are like vectors. They have magnitude and directions, but they are function of the coordinate plane. So coordinate frame. So here we can see that we have some kind of moment tensors. So these tensors, they are parallel to vector 1 in the first panel, but they are either lying along vector 1 or they are lying in the vector 1 and 2, this particular plane, but they are not lying in the plane 3, and in this case they are lying in the vector plane 1 3. So in this vertical plane these vectors are lying, they are perpendicular to 3, but they are not lying in the plane 2. So when these tensors are lying in this plane, so we have three cases here. Similarly, these tensile tensors, they may be parallel to vector 2, and they may either lie in the plane 2 3, like here we can see they are lying in the plane 2 3, they are they are lying in the plane 2 1, they are perpendicular to the vector 1 and they are parallel to 2, but their component along 3 is 0. Similarly, here they are lying only along the axis 2, there is no component in the other axis, and here they are lying along the axis 2 and 3, they don't have any component along 1. So tensors are like vectors and they are function of the reference frame. Similarly, in the third panel here we can see that these tensors are, they are parallel to 3 and they are lying, in the first case they are lying in the plane 3 1. So here they are perpendicular to 1 and they are parallel to 3, but they don't have any component along 2. Similarly, here we have the vectors which are lying in the plane 3 2, they are perpendicular to the vector 2 and they are parallel to 3, they don't have any component along 1, and in this case they are lying along axis 3. So we can see that the output of this will be this kind of moment tensors. So we will have 9 kinds of moment tensors for the for fault plane solutions. Now these are like the stress strain tensors. We already discussed stress strain tensors in class. So the moment tensors are also described in terms of 3 orthogonal axes. So we can see that the tensor along which this tensile stresses stress occurring, this is the tensile axis here. The other axis, this other axis will be P for a compressive axis and N for a null axis. So if this is the tensile axis T, then either 2 or 3 is the compressive axis, and whatever is left, if 2 is the compressive axis, 3 is the null axis, or if 3 is the compressive axis, 2 is the null axis. So which one will be tensile, which one will be null, and which one will be compressive, that will depend on the fault plane, what kind of movement has occurred in the fault plane, and what is the orientation of the fault plane. So the FPS finally gives us the direction and the magnitude of the 3 axes, that is the P, T and N. So why we bother for this direction? So what we generally get from these directions? Actually, the orientation of this axis of a moment tensors is of interest for structural geologists, because the fault surface along which the earthquake was generated is 45 degree from the P and T axis. So if we know the direction of the P and T axis, we can very easily calculate the direction of the fault plane. So it also contains the N axis. So let's come to the figure below. Here we can see that suppose we have the P axis in this this is the hemisphere, where we see that the P axis is in the bottom part and the T axis is in the right hand direction. So the fault plane is at 45 degree to the P and T axis, but there will be one more plane which is also at 45 degree to both these axes. So this plane which is occurring perpendicular to the fault plane, this is called the auxiliary plane. So generally, although we get the fault plane from the FPS solutions like the PT and N axis, but there is one more plane which will come from these solutions, that these two planes are called nodal planes. So out of these two planes, one is the fault plane and other is the auxiliary plane, but there is no way for us to understand what is the which one of this is the fault plane, unless we have some kind of field evidence to find out that yes, this exactly is the fault plane. Now, one of the most important thing that we will see at next is that if we project this particular fault plane and the P and T axis into the bottom hemisphere, then we will see that suppose we are projecting this to the bottom hemisphere, and the projection will have a central white region which will be the center of which we will get this P axis, and in both the sides we will have these gray regions, and we will have the T axis at one edge. So this projection which we will get by projecting this into the southern hemisphere, this will be represented in this form. So here we can see that the P axis is lying at the center and T axis is in the right hand side, and we have these two gray regions in both the sides, and the P, that is the white region, in the center. So this particular representation which we get by projecting this fault plane solutions, the planes as well as the axis, into the southern hemisphere, this is called the beach ball. So this is one of the most important thing in the FPS. So beach ball is the final representation of the outcome of the FPS. So why it is termed beach ball? It actually looks like a ball which we generally use for playing in the beach. That beach ball will have a different colors like black and white. So this looks like a beach ball, so we call it a beach ball. So this ball will be oriented in the direction of the strike of the fault. So if this fault here is a north-south orientation, so we will get a north-south striking planes. Suppose this fault is oriented in the northwest southeast direction, then in that case the beach ball will slightly get rotated in that direction. And from the field evidence, if we come to know that this actually is our fault plane, we'll know the strike and dip of the fault plane also. So how we know? Suppose we have this particular great circle as the fault plane. So the points where this particular great circle will intersect the outer edge of this projection, these are the two outer edge. So here this great circle is intersecting here. So if we join a line, that will give us the strike, and the arrow which if we draw an arrow from the strike towards the great circle, that will give us the dip direction. So it will be perpendicular to the strike. So if we know the fault plane, we can find out the dip and strike. So similarly we can find out the dip and strike of the auxiliary plane also, but of course that is not much important for us. Now what we see here is that the FPS, it gives us the fault planes, the auxiliary planes, and the axis. So this TP and the N axis, that is the tensile, compressive, and the normal axis. So this can be plotted in the this particular beach ball diagrams, and from this beach ball diagram we can have an understanding of the orientation of the fault plane. So now we have understood what actually is a fault plane solution. So what it gives, so basically fault plane solutions is it gives the mechanism of how the faulting has occurred, and that has led to the formation of the earthquake. Now the output of that FPS solution is represented in the form of a beach ball diagram. Now looking at the beach ball diagram, what are the things that we can understand about the falls and their sense of movement? So we will try to understand that in this coming slides. So generally we know that there are different kinds of falls. So we have strike slip falls. So in strike slip falls we do not have any component of dip component is 0. So naturally those falls will be vertical, so we will get them as straight lines. There won't be any kind of dip component there. So basically when we have a strike slip fall, so we will get the vertical auxiliary planes, and this can strike. In this case we can see that they are striking in the north south or east west direction. So this, in this figure A, we are seeing two vertical auxiliary planes. They are striking in northeast and in the north south and east west directions. Or if the fault is striking in some other directions, then this will be oriented as per the strike of the fault. Now coming to the next important thing that we already have understood, that along the direction, along different quadrants of the of this fault plane, we get compression and tension. So the the beach ball, the dark component, the dark circle, the quadrants which are represented by the dark shades, there we see that we have a tensile kind of tensors there. So these are moving away from each other, but the white quadrants, they have compressive tensors. So from the beach ball diagram, from the shades of the beach ball diagram, we can understand which quadrants are the tensile quadrants or which quadrants are the compressive quadrants. Or rather, if we know the compressive quadrants and the tensile quadrants, we can draw the beach ball diagrams like this. Now from this beach ball diagram, we can also understand the sense of movement. So the how the sense of movement, one easy way to understand how the sense of movement will be, uh, the movement will occur from the white quadrant to the black quadrant. So if this is our fault plane, so it will be, the arrows will be pointing in this direction. So the top arrow will be pointing in the right hand direction. Similarly, the bottom arrow will be pointing in the left hand direction. Now if we stand in any of the block and we see the front block from there, suppose we are standing here, we will see that the block here has moved in the right hand direction. Similarly, if we stand in the upper block here and if we see this one, there also we will see that this block is moving in the right hand direction. So we will call this as a right lateral slip. So in this beach ball diagram, if this color represents the compression and the tension, so the dark color representing the tension and the white color representing the compression, the sense of movement will be from the white to dark color, which will represent the right lateral slip along the fault. But if on the other hand the north south is our fault is our fault plane and east west is our auxiliary plane, then we will see that the arrows will again move from the white to the black quadrant, and if we stand on this quadrant, we'll see that the block has moved towards our left. Similarly, if we stand on this quadrant, we'll see that the block has moved towards left. This block has moved towards our left. So there are possibilities that either this can be our fault plane or this can be our fault plane. Which one is the fault plane, we will come to know only from the field evidence. So there are two likelihoods. One is that either it can be formed by the right lateral slip along a east-west fault like this as seen in the C, or it can be formed from the left lateral slip along the north-south fault. So if we get a beach ball which is having two vertical auxiliary plane, first thing we can say is that this is a strike slip fault. And from the quadrant, if we come to know this is the tensile zones and these are the compressive zones, then we can easily find out what is the direction of movement. So this is the advantage of using a fault plane solution, or rather the beach balls which we obtain from the fault plane solutions. Once we look at the beach ball, we can easily come to know what is the fault and what is the sense of direction. So this is for the strike slip fault. Now next let us see if the fault is a dip slip fault. Now similarly, if we have a dip slip fault, if it is a normal fault, so in the normal fault, the hanging wall, that is the wall which is sitting above the fault plane, this is moving down. But in the reverse fault, the hanging wall is moving up. So what kind of beach ball do we get? In case of normal fault, we get a beach ball where we have the compressive axis in the central part. So we have the white part in the central part, and in the side we have the gray region, that is the tension. But in the reverse fall, the beach ball will be opposite. Here the tension will be tensile stress axis will be at the center, and the compressive will be in the border. So we will get the gray color or the tensile zone in the center. So the center of the beach ball plot is white, then we can say this is a normal fault mechanism. Similarly, knowing the direction of the fault, we can find out the deepen strike also. Similarly, if we see the beach ball diagram having a black center, then we know that is either a thrust or a reverse fault, and we can find out the deepen strike of that reverse fault. So next, coming to the oblique faults, here what happens, here the fault has a normal as well as a strike as well as a deep component. So if the fault has a normal component, then like before, here also we get the central region as the white color. But if the fault has a thrust component, like the hanging wall block is moving up, in these cases we have the black color, the gray color in the center. So we have the tensile region in the center and the compressive in the borders. So we can simply find out what is the orientation of the axis, and we can find out what is the orientation of the fault plane and the auxiliary plane, and from the first recording of the seismic wave we can find out which is the compressive zone and which is the tensile zone. So from there, if we draw the beach ball, we can easily find out the type of fault associated with it and the sense of movement. But obviously we will require the field data to identify which is the fault plane and which is the auxiliary plane. So basically, to summarize what we have understood from this, that actually FPS gives us the fault plane which led to the deformation from which the earthquake has generated. So assuming that the fault plane can be differentiated from the auxiliary plane based on the field evidence, the FPS provides the structural geologists with the orientation of the fault plane, the direction of the hanging wall. Hanging wall is the block overlying the fault plane, and the direction of the slip. So we will come to know whether the associated fault is a strike slip fault, reverse fault, or a normal fault, or an oblique fault from the beach ball diagram. So basically what we get from the FPS solution is the mechanism by which the earthquake was generated. So which was the fault that led to the formation of the earthquake? So what is that going to help us? So the understanding the type of deformation associated to the earthquake, or that led to the formation of the earthquake, helps in the assessment of the active tectonic activities in the region, and this can also help us to make the decisions for designing or construction purposes. That means, suppose we want to build a bridge. So we know that this is a tectonically active area. If we have the fault plane solutions of our previous earthquake, we can find out where the movement previously occurred, which are the active faults present in the region. So that will help us to find out which are the locations suitable for our construction. Suppose we want to construct a bridge or a railway line or a highway, we will not construct it over the active fault to the extent possible, because if an earthquake occurs, there are chances of movement along that fault that may lead to the rupture of the bridge or the highway or the structure. So basically this seismotectonic activities can give us a very thorough understanding of the active faults present in the area, and kind of precautions we need to take to construct any structures in that region. So this is all about FPS. So I hope you have got a thorough understanding. So thank you for listening, and if you have any queries, you are most welcome. You can ask the doubts in group and I will answer them. Thanks.